Okay, hello everybody. So I just want to summarize weeks 1 and 2, where we learned about maps, and also we learned about vectors. So whenever we answer or solve problems, there's always sort of three things that we could do. We could use the cartoon pictures to think about the problem. This is sort of a visual way. We could use words to think about the problem. This is good when we're communicating with each other. And sometimes it's easier just to say it in words than write it out. But then there's formulas, and the formulas are the things that we have to give to a computer. The formulas are usually harder to understand, but they're necessary in order to, for example, predict the results of an experiment. Before the experiment, you would need to use the formulas and calculate with them. So formulas are sort of what we're really going for, and the cartoon pictures and words can help us understand the formulas. And so because the formulas are so hard, for me, I'd like to take some time to explain some common errors that I've been seeing and that I made myself when I was a student. Okay, so here you can sort of see the cartoon of stretching a vector or shrinking a vector, which is really a scalar multiple times a vector. And here we see, here's a formula. It's sort of a shorthand way to write this. So these mean exactly the same thing. It's just that the formula is easier to write because it's shorter. C, and the way we read it is C is an element of the set R. So the set R is the real number set. So it just means C is a real number. It tells you like what kind of object is C, because we often need to figure out if it's a real number or if it's a vector. So here I'm telling you that when I wrote V, what I meant is a vector. And I even told you the dimension of that vector. V is an element of three-dimensional space. And so in words, this is what those symbols mean. Except, of course, the symbols are much shorter to write. And so then a consequence of this is that the formula CV, or C times V, scalar times vector, is the result of it is again a vector, because we took some vector and we scaled it by C, we get another vector. For example, it is not a real number. CV is again a vector in three-dimensional space. Okay. Here's some more examples of here's the cartoon pictures of what's going on. We took this purple real line and we put it into space in sort of a twisted cubic, it's called. And in formulas, this is a map. Like in a computer, this would be a function or a map. And the function has inputs and outputs. And so we create a name for the input, and here is the specific formula for the output. Now, in words, here's the picture, here's the formulas, now here's the words. A map F sends the real line into three-dimensional space. The image of F looks like a twisted curve. Okay, and the way it sends is precisely this formula. So to try to describe this in words it'll just take a lot of words, and it's unclear if you'd even communicate. But with the formulas, it's shorter and it's precise, and you can calculate with it. You can predict experiments, for example, and see if you're correct. And now this is tricky. Here are these parentheses. Does this mean F times 2? Well, no, because we said F was a map. So then these parentheses actually mean that we can say them F of 2 in words. Here's the formula. But what we mean is F evaluated at the input t equals 2. And so that's what these parentheses mean. They mean evaluate the function F at the input t equals 2. they don't mean multiplication. Whereas like if we wrote 5 parentheses minus 3, here the parentheses mean something completely different. They mean that we're supposed to multiply these numbers together and get out a new number. And so this was confusing to me. Here, the key here is that I know what is f. I have to know what f is, and so that's why I usually write down something like this. F is a map. Then I know that the only thing these parentheses can mean is that I'm evaluating the map f at an input. I'm not multiplying numbers. Okay, and then again, here's parentheses. So even more parentheses, and this time they mean something different. So here, I'll move this in. Here, the parentheses mean they're sort of like a container to hold our 3 coordinates and let us know, like, hey, this object is in 3-dimensional space. And so we put it in a container that has 3 positions. And that is the use of parentheses right there. Those are the parentheses. And they don't mean multiplication. They mean multiplication up here, but they mean a container for our 3-dimensional vector, or 3-dimensional point. Point and vector are sort of the same thing, point slash vector. And so we're seeing that if we evaluate the map f at the input 2, our output is 3-dimensional, namely given by this formula up here. So we plug in a 2, and what we would get is a 2 squared, and a 2 to the 3rd power. And so it's really hard because you use parentheses to multiply numbers. Sometimes you use them as a container for a higher dimensional point, and sometimes you use them to evaluate a map at a certain specified input. Okay, and we could also write that f evaluated at the point 2 is an element of 3-dimensional space. So like the output here is a vector, and that we're just saying that. We're just saying the map f evaluated at the input 2 produces the output f of 2, which is a point in 3-dimensional space. And that's this piece. It's saying which is a point in 3-dimensional space. Sort of letting us know, where does this thing live? And why does it live there? Well, because f was a map. And we wrote down that map specifically, and it has 3 components. So it lives in 3-dimensional space. So again, like all these different ways to have parentheses. Sometimes they mean multiply numbers. Sometimes they're a container for a 3-dimensional point. Sometimes they're evaluating a map. And it's really important to know which one is which. And to say, when you're writing your own formulas, you need to say which one is which. You can't just write f of 2 without telling me what f is. You have to tell me that f is a map. Okay. And now here's one more thing. So down here I have parentheses yet again. And here the parentheses they're sort of like multiplying because you're scaling this vector. This is where, I have to tell you what is v2, what is v3, what is v1. I have to tell you that. And I do down here. I say where each vi, v1, v2, v3. So I here is an index. It's standing for 1 and 2 and 3, just all of them at once, so that we don't have to write each one separately. Otherwise, I have to write, well, v1 is a vector in 3-dimensional space. v2 is a vector in 3-dimensional space. v3 is a vector in 3-dimensional space. So instead, I just say each vi is a vector in 3-dimensional space. And then maybe I could tell you specifically what are those vectors. v1 is this vector 2, 3, 7. v2 is this vector 0, 0, 5. And v3 is this vector negative 1, 0, 1. And so why did I put parentheses here? Well, sometimes when you have a negative number, you like to put it in parentheses to just kind of view it as one unit, as one number. And this is nice because then we can just use plus signs everywhere. For example, in our formulas, C1v1 plus C2v2 plus C3v3. Then here, C2 would be the number negative 3. And that way, the plus matches up with the plus here. And so here again, parentheses are used in yet another way, sort of to, I guess, as a container to put this number and think of it as a one number, a negative 3. And here's yet another way parentheses are used. Here we're defining a map. I didn't give it a name. I could give it a name like gamma or like G. And then, what's the formula of the map? It takes two numbers, so the map goes from R2 to actually R3, because now I'm using parentheses here to hold the contents of a three-dimensional vector. I could have written 2, 3, minus 1, but sometimes it's nicer, especially when we're multiplying a vector by some number. So here T1 is a real number. And when I write R2 above T1, T2, that's sort of telling you that that this is an element of R2. Okay. And, so this is yet another way that we use parentheses to hold a vector sort of written as a vertical column. Identically, we could write T1 times 2, 3, minus 1, plus T2 times 1, 0, minus 1. And here I'm separating the three components by commas, and I'm putting them in the container, which has parentheses. And these are identical things to do. Alternatively, I could write it as like something, 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 so it's clear the output is three-dimensional, although here it also should be clear once we get used to this notation. And what would I do? I would have, 2 T1 from here, plus a T2 from here. So this is the same formula. This is the same formula. Now, what's my second position of my output? What's the second formula of the output? Well, this time it's 3 T1 plus nothing, plus 0 T2. What's the third position? Well, it's minus T1 minus T2. And so these are, three different ways to write the same formula. And yet another way that parentheses happen, here it's like a container, because I want to make clear that I need to get a number out of here. So like if T was 0.2, then this would give me 0.2 times P1 plus 1 minus 0.2 would be the number 0.8. So if I didn't want to calculate it yet, I just wanted to write it down like this, then I could use the parentheses. And here the parentheses are a grouping or a container holding this number, which I haven't yet fully calculated, and which I could calculate next in maybe the next line by saying like this. And when you have decimals, sometimes it's even nice to put them in parentheses, just to make it more visually clear what the scalar is and what the vector is. Here, I'm assuming that P1 is some vector, maybe in two-dimensional space, and also P2 is some vector in two-dimensional space. And I haven't given you the precise coordinates of P1 and P2 yet in this formula. Last couple things. Here parentheses occur again, and this time, like in a computer, they're holding the inputs. So these are inputs to the function, which is the dot product function. And the dot product needs two vectors. In particular, these are all ways to write dot product. The dot product of, if V was in R2 and W was in R3, the dot product of V and W is not defined. It would be meaningless, okay? So the two vectors in V dot W have to be in the same dimension. Otherwise, it doesn't make any sense, right? Because the formula is, the first components multiplied and added to the second, to the second components multiplied and added, to the third components multiplied and added. But if W3 has a third component and V does not have a third component, like, what are we going to do here? What is V3? It doesn't even exist because V is only a two-dimensional vector. Okay, so for example, if V was negative 2, 3, and if W was 5 minus 1, 5 minus 1, 7, we cannot do V dot W. We cannot do it because 7 doesn't have anything to pair with. And so just the dot product isn't defined. Same for the cross product. The vectors have to be, now this time, they have to both be in R3. So V needs to be a vector in R3, and W needs to be in R3. This is the formula for W is in R3. Right? And here the cross product is now a function, or a map. It takes two vectors as input and spits out now a vector. So that's a big difference. So I would say that the cross product, the output of it is again a vector in R3. The dot product, the output of it is always a real number. So the dot product of two vectors is a real number. The cross product of two vectors is a vector, and they all have to be in three-dimensional space for cross product. Okay, so notation and formulas are very tricky, but that's why we always try to connect them to the cartoon pictures and to the words, and make sure we know what the formulas mean in words, and also make sure we know what the formulas look like, at least roughly, in some sort of a cartoon picture. Okay, so we already gave cartoon pictures for maps. Let's try to give some cartoon pictures for this. Okay, so what is the cartoon picture of, let's say, a linear combination of three vectors in R3? Well, if I have some vector, some other vector, and a third vector, what I'm going to do is scale the first by 2, scale it by 2, and then scale the second by -3. So scale the second by -3. So I'm going to label it as -3v2. Here's 2v1. And then scale the third by pi, which is roughly 3.14. Okay, so this is pi v3. This is my cartoon picture of this formula. And then I need to add them together. So I need to add them together, which means what I do is I start here, and I first move along 2 of v1, and now I'm here. Then I move along -3 of v2, and now I'm here. And then I move along pi of v3, and I end up here. And so my final answer is this red vector. So it's equal to that red vector, which has some components that I could figure out, namely by using this, scaling them, and adding them. Okay. So, good. Maps, vectors, parentheses used in lots of ways, cartoon pictures, formulas, and words, all sort of coming together.